Okay, so work and energy, or work-energy theorem. Probably the single most important concept in high school physics. Okay? It is because of work-energy theorem that all things happen, because nothing can happen without energy. Okay? You can't do work if you don't have energy. You also can't change energy without doing work. Catch 22. Okay? They rely or depend or are the same thing. Okay? Just because of the nature of the work-energy theorem. So, first off, we have to understand what work is. Okay? And usually when I ask that, the first thing people say is they spit out this formula that they learned last year. Work is force times distance. Well, that's how you calculate work. That's not what work is. Work is a change in mechanical energy. That's what work is. Okay? If I do work, I change the mechanical energy of something. Okay? Or a system, or whatever. Okay? But I change the mechanical energy. Now, if I'm changing the mechanical energy, that means I'm doing one of two things, or both of them. Okay? If I'm changing mechanical energy, what is mechanical energy made out of? Potential energy and kinetic energy. So if I do work and I change the mechanical energy of the object, I will have either changed the potential energy, the kinetic energy, or both. Okay? Now, that's all well and good to say that. What does that look like? If I do work on this chair, okay? If I'm going to do work on this chair, obviously I'm going to have to exert a force through a distance on this chair. What's going to happen to it? It'll move, right? Depending on what kind of work I do and what direction the force is acting. I mean, if I pick this chair up and I throw it, which I wouldn't do today, okay, then its change in energy is going to look considerably different. If I do something just kind of calm, cool, and collected, like push, okay, what I see is what kind of energy about it changed.
It changed from potential to kinetic.
Okay. It did have a change in kinetic energy, but there actually wasn't any potential energy here. Okay? All I did was do work on it. Okay? I exerted a force on it through a distance. There was never any potential energy for the chair. Okay? There was some chemical potential energy within my body and from the food that I ate that became sugar, and my muscles metabolized that and allowed me to exert the force, but that's biology. We don't deal with that. Okay? All that we're looking at is that I exerted a force through a distance when I push. Okay? Had I exerted a larger force, or had I exerted that force over a longer distance, would that have looked different for the chair? Yeah, a bigger force means the chair goes farther and faster. Okay? Or the same force, but I take a run at it. And then let it go. Okay? Then it obviously goes farther. Okay? I changed one or the other of the two factors that affect how much work I do. Okay? I either exert the same force over a greater distance or a greater force over the shorter distance or the same distance. Either way, I change the energy more as a result of that. Okay? So that's the relationship between force and work. Greater force or work. Okay? Depending on the situation, work and energy can be equal. That's the work-energy theorem, because work is a change in mechanical energy. So if I do 300 joules worth of work, I'm going to change the mechanical energy of the object or system by 300 joules. Okay? Assuming it's a perfect physical world and no energy is lost to anything else. Obviously in that system, not all 300 joules were transferred to the chair. Where did some of it go? Friction. Yeah, you could hear the chair's wheels sliding on the floor. Okay? Sound is a form of energy. Obviously that energy came from the work that I did. It's not making any sound now. Okay? So some of the energy that I used, some of the work that I did, became sound energy. Okay? Probably became heat as well. Right? It didn't all go into the chair. And that's what we have to realize. In the real world, not all of it is actually doing the useful work that we want. The more of it that does the useful work, the more efficient the system is. Okay? And we're always looking for ways to make things more efficient. And you learned about efficiency a little bit in Science 10 as well. Okay? That's how much of the work you put in actually changed the mechanical energy of the object. Okay, questions so far? Right, hopefully this is seeming really familiar because you took it in Science 10 and you saw this lesson while I was away. Okay. All right. So strictly speaking, work is done if you exert a force through a distance. Okay, that's that whole work is F times D thing. Now we do complicate this formula slightly in Physics 20 to reflect the fact that force is a vector quantity. Oddly enough though, the thing we're calculating, work is scalar. Okay? Work is either in or out. You're either putting work in or the system is doing work, that's work out. Okay? One or the other, but it is not vector. When I do work on a system, it gains that energy. That energy can do anything, become anything, go any direction. I don't have control over that necessarily. Okay? So work, because it is related to energy, which is also scalar, okay? Work is scalar, energy is scalar. Right? So in this diagram here, we have this constant force being pushed, being used on this stalled car, okay? Because the force and the displacement are in the same direction, theta is 0, right? There's no angle between that force and the displacement. So as a result, theta is 0, and what's the cos of 0? 1. Okay, so it doesn't have any effect. Now, when you really look at this person, they're not really exerting a force in the direction that arrow is pointing. Now, it looks to me like their arms are pointed down slightly. So is actually all the force they're exerting doing the useful work they want? No. Okay? I don't know why anybody would push downwards on a car when they wanted to go forwards. Okay? I would, lean down like this, bend my legs. I mean, they've got their legs bent, but their arms are really in the wrong position to do the work that they're looking to do. Okay? I would want to push more forward on the car. Maybe I put my back into it, back up. Probably not, my knees are shot, they probably hurt. Okay? But I would want to get all of my force directed in the right direction. Okay? The more force I exert in other directions, the more I waste. Okay? The more of my own energy I waste. Okay. Right, so scalar quantity. Okay. Now, units for work are in Newton meter because obviously we're multiplying force, which is in newtons, by distance, which is in meters. So we get Newton meters, which we abbreviate joules. Okay, it's important to remember that it's a Newton meter. Okay, but it is actually just called a joule, okay, at all times. So units for work, units for energy are joules. Most common mistake I see on exams: people write newtons for the units for energy. Okay? Remember, newtons are for force, joules are for energy. Okay? All right. Those people doing any work? They can push on that rock all day, ain't going anywhere. Okay? Why do they get tired? If they're not doing any work, they're not transferring any energy to the rock, they still get tired. Right, they're exerting a force on the rock. What's the rock doing? It exerts force back. Bracing yourself against that reactive force, okay, is going to require work, right? So if I push on the wall, okay, I push on the wall like this, okay, as soon as I start exerting a force, I'm using my muscles. What do muscles do when you use them? They contract, right? As soon as you flex your muscles, as soon as you use your muscles contract. Okay? Is that the distance over which the force is being exerted? It is. That's the force back on you. Okay? I'm exerting a force on the wall exerts a force back on me, and in order to keep from moving, I have to brace myself, and the movement now becomes the contraction distance of my muscles. My muscles stay clenched, I continue to exert a force, and I get tired. Okay? The wall is actually doing work on me. Okay? And I'm bracing for it. Okay? That's why I get tired. I can push all day, I'm not going to change the energy of that wall. But I am going to change the energy of my surroundings. Because if I continue to push, I'm going to get hot and sweaty. Okay? Thermal energy will be the result of all the work that I'm doing. No mechanical energy, but thermal energy instead. Okay. So, like we were saying here, force and displacement don't always point in the same direction. Okay? Sometimes in order to make work easier, I actually exert a force slightly off from the direction I want the work to be done. Okay? This is like when we're talking about rolling this luggage carrier, okay, or if I'm moving a heavy object, if I'm having to drag something really heavy, I generally don't pull horizontally along the floor. I'm going to pull a little bit in what direction? Okay? Because by pulling up a little bit, I reduce the amount of friction that's involved, and I make my work a little bit easier. I still have to exert the same amount of force, okay, in total, but at least I get the desk to move. Maybe if I don't do that, I can't overcome the force of friction in the desk where the heavy object doesn't move. Okay? So I sometimes have to do that. All right. Now, if that's the case, that's where this whole F times the cos of theta thing comes in. Even though this lady is pulling the box at an angle, the box isn't moving that way. She isn't doing any work in that direction because there's no change in energy along this vector. The change in energy that's occurring is along this vector. So only this component of the force is actually doing work. Okay? There is certainly a vertical component to this force. But because the height of the object doesn't change, she isn't changing its potential energy in a vertical plane. Does everyone follow me there? If she's not changing the energy in that direction, there's no work done in that direction, and that's why this formula contains that cos of theta part. Okay? So that we're only using the force that's actually doing the work, or the part of it that's doing the work in that calculation. Everyone okay with that idea? It's very rare that we ever end up with a question where we have to do this cos of theta thing. Okay? Most of the time it's just calculating the energy and the work and such. Okay, so what we would do here to calculate the work that she is doing in dragging the luggage carrier, okay, F is cos of theta times D. So 45 newtons was the force she was exerting at a 50-degree angle over 75 meters. She's going to do 2.17 times 10 to the 3 joules worth of work. Okay, she's burning a lot of calories. That's a lot of energy. Okay? I'm lucky if I burn that many calories in a day. Okay? This is like a really heavy box, or there's a heck of a lot of what? Well, it's only 75 meters. Friction. Yeah. I don't know that those wheels are working very good. Okay? To use that much energy to move that box, okay, it's either a really, really big box or there's a lot of friction. Okay? Now, if she drags that at a constant velocity, does she change the kinetic energy of the box? No, she doesn't. Okay? Because a change in kinetic energy, remember, kinetic energy is 1/2 mv squared. If I don't change v, then I don't change the kinetic energy any. But she'd still be doing work because she'd be working against. Anytime you drag something, what are you working against? Friction. Yeah. Okay? So she'd still be doing work, just not so much on the box, just against friction. And that's the case most of the time when we drag something. Okay? We're dragging something, we're just dragging it. We're not accelerating it. Okay? We're just getting it to move. All of our work that's being done is just to overcome the force of friction. Okay? If I accelerate something, then I'm doing mechanical work that is changing the kinetic energy of that object. Okay? Only if I accelerate it. Now, if she's dragging it at a constant velocity, what's the net force? 0. Okay? If there's no net force, then there's no acceleration, thus there's no change in velocity, thus there's no change in kinetic energy. Okay? That's those situations where you would know all the work being done is just turning into heat, sound, or whatever, because it's not changing the mechanical energy of the object. Okay? It isn't speeding up or getting higher off the ground. Both of those things imply, or indicate, sorry, a change in mechanical energy. It's either going faster and kinetic energy is increasing, or it's getting higher off the ground and potential energy is increasing, or both. Okay? But if neither one of those things is happening, all the work being done is just turning into energy that's going to the surroundings, okay, in other forms. All right. Person lifts the barbell. Okay, they push the barbell up. The barbell has a weight of 710 newtons. If I want to move it at a constant velocity from my chest to the extended position of my arms, okay, 0.65 meters, what kind of energy am I changing about it? its potential energy, right? I didn't accelerate it, I moved it at a constant velocity from my chest to a full extension of my arms, okay? All I'm doing is changing its potential energy, okay? I can calculate that by simply going force times distance, okay? And when we're doing that, okay, F times the cos of theta times d. Okay, so that'll be our 710 times the cos of what angle? 0. I'm exerting a force in the same direction the barbell is going, straight up. Okay, there's no change in angle here, so cos of 0, okay, times the distance, which is 0.65. So 710 all right, so I do 462 joules worth of work. I change the potential energy of the barbell by 462 joules. Is the barbell now dangerous? Yes. The barbell now has the potential to do work. If I drop the barbell, said work will be on my rib cage. Probably bad. Okay? So, I don't want that to happen. I want to lower the barbell slowly. In fact, I want to lower it at a constant velocity back down to my chest safely. Okay? What direction do I push? Up. Yeah. I'm still going to push up, but which way is the barbell moving? What angle is that? Not 90. 180. I'm pushing up. The barbell is moving in the opposite direction of the force I'm exerting. Okay? So the barbell is now moving at 180 degrees to the direction that I'm pushing. Okay? I'm lowering it. Oddly enough, I use the same amount of force to raise the barbell as I do to lower it, if you're weightlifting properly. Okay? Way too many people think it's all about the upward motion. Okay? And then they weightlift like this. And they just don't do anything. You're losing half the workout. Okay? If you're not lowering it at the same speed you raise it, you're only getting half a workout. Okay? It's ridiculous. I don't know why people bother. Okay? Lower it slowly. Exert the same amount of force to lower it. Okay? You get twice the workout. All right, so I'm lowering this force. So now I've got F, cos of theta, times d, but now that's 710 times the cos of 180 times 0.65. What's the cos of 180? -1. So, is the barbell losing energy? It sure is. Once it's back down on my chest, it doesn't have any potential energy anymore. Okay? It gives it all back to me. And I have to do work to resist it as it comes back down. Okay? It loses energy, so that work is negative. Now, you're probably thinking, Coder, you just told me work was scalar. I did. Work is scalar. But remember, there's positive work, that's work that goes into a system, and there's negative work, that's work the system does on something else. If it's doing work, it's losing energy, or it's transferring that energy away. So when I did the work on the barbell, I gave energy to the barbell. When I lowered the barbell back down, it gave it back. Okay? It doesn't have any more once it gets back down to me. So work can be positive or negative depending on whether the work is being done to the object or by the object. Okay? Everybody all right with that idea? Okay, so that's all the reasoning there that we just looked at. So we get a negative number because obviously it loses that potential energy after I lower it. Okay, so in order to do work, you have to have energy. That's the work energy theorem. Okay? Work is a change in energy. You can't give away what you don't have. Work is not like a credit card. Okay? Where you can spend even though you don't have the money to pay it. You can't do that with energy. Right? You either have it or you don't. Simple as that. Okay, so that's the work energy theorem. Basically it says that energy is needed to do work because work is a transfer of energy. Okay? If that work is done, the object being worked on gains that much energy. Okay? The other things we have to remember, the two types of energy, okay? Kinetic, which is dependent on mass and speed, and potential, which is dependent on mass, acceleration due to gravity, and height. Okay? Are they all right with those ideas there? Hopefully that's review of science said. All right, so we're going to do a few examples here, guys, of work energy theorem type questions and see how we do. Now, in Science 10, you'd have had really easy work energy theorem questions like, you put a bow and an arrow and you exert this much force to draw the arrow back this far. How fast will the arrow go when you release it? Well, it was just how much work you did equaled the kinetic energy of the arrow. Okay? They're very kind of one-dimensional, very simple types of problems. Okay? In Physics 20, we're going to be looking at ones where both types of energy change, both potential and kinetic. Okay? Where it might be on an incline or something like that. Okay? It's still the same principle. Work is still going to be a change in energy. We're just going to be looking at more detailed examples. Okay, but we're not going to do that one. All right, so here's a simple one. Okay, pull a sled along a horizontal surface, applying 620 newtons of force at a 42-degree angle above the horizontal. How much work is done to pull the sled 160 meters? All right, so what did they give us? Force. They gave us theta. And they told us distance. Okay, pretty easy one to use. I'm trying to find the work done. What's the formula for work? Well, F times cos of theta times d, right? I can go force times distance as long as the force and the distance are parallel. Okay, but in this case they're not, so I'd have to plug in that angle as well. So I take my 620 newtons, multiply it by the cos of 42 degrees, and then multiply it by the 160 meters over which the sled is being dragged. Okay, and I should get 7.37 times 10 to the 4 joules. Okay, this is like obviously a very heavy sled that should have had a team of dogs attached to it. Okay. That's a lot of energy, that's a lot of work. Okay, here's the second part. It's not in this question. It's on the page, the question doesn't have a second part, but I'm asking you a second part. If there was no friction, how fast is the sled going now? Sorry, we don't know the mass of the sled. Forget it, can't do that. Have to know the mass of the sled to do that. Okay. Some of you guys try 2, 3, and 4. I'll make them bigger so you can read them. Okay, you guys try 2, 3, and 4. I'll give you a few minutes, then we'll walk through those. All right, so for number 2, okay, we have a force that's acting at an angle of 30 degrees, so we know what theta is. Okay, relative to the direction of displacement, the force required to do 9,600 joules, so they gave us the work this time, okay, and we're looking for the force if that force is exerted over a 25-meter distance. All right, so F times the cos of theta times d equals work. Okay, I'm looking for the force, so I'm simply going to divide cos of theta times d over to the other side. Okay, and that will leave me with the force, so that'll be 9,600 joules divided by the cos of 30 degrees times the 25-meter distance, and that should give me 443 newtons worth of force. Everybody all right with that? All right, how many people are done number 3? Okay, do we need to go over number 3? Yes? Okay. All right, so on number 3, we have a force of 640 newtons. Okay, it's doing 12,500 joules worth of work. We're looking for the angle if the distance is 24.0 meters. Now for this one you have to do an inverse cos in order to actually get the angle. Right? So what we've got here is work equals force times the cos of theta times d. And I'm trying to get theta by itself. So the first thing I'm going to do is divide force and distance over. Okay? That's going to leave me with the cos of theta. I'm looking for theta. To move cos over, I've got already the hypotenuse, or sorry, the adjacent side over the hypotenuse here. Okay, so all I'm doing is bringing the cos over. So it'll be cos to the -1 times, or of, sorry, work over FD. Okay, and that will give me my theta. All right, so that'll be our 12,500 joules. So we'll go cos to the -1 of 12,500, okay, divided by 640 times 24. Right, so we get 36 degrees, okay, as our angle there, 35.5. All right, how many people have done number 4? Okay, do we need a little more time on number 4, or are we stopping? Just a little more time? Okay. Okay, there's a quick way to do number 4. And if it's you can figure it out if you understand work energy theorem. What kind of energy about the bungee jumper is changing here? Yeah, well, their potential and their kinetic. One is turning into the other as they fall. Everybody okay with that? Okay, so if work is a change in energy, can I calculate the work done by gravity by simply saying that the work done is equal to the change in the potential energy of the bungee jumper? I can. Okay, so all I have to do is say work equals m times g times the change in height. What's the change in height? 20 meters. That's how far they fall. Do I know their mass? Do I know gravity? Okay, so this is the quick way to do this, okay, is just to go 60 times 9.81 times 20 meters. Okay, and that'll give us our 1.18 times 10 to the 4, whoa, 10 to the 4 joules. Okay, if I understand work energy theorem, that's the way I do it. If I don't understand work energy theorem, then I might go about this a completely different way. And I might try and find, like, use their acceleration to find, you know, the net force, and then multiply the force by 20 meters, and I'm going to end up with the same number. I'm going to do a lot more work. Okay, and I see people do that all the time in other types of work energy theorem questions. Rather than using work energy theorem, which is work's a change in energy, they go in and they find all these extra forces that takes them forever to find. Then they're multiplying those forces by distances. They're putting them together. They're doing all this extra work when all they had to do was say, work's a change in energy, and calculate the energies. Okay? In the fall of last year, okay, because we didn't have a unit exam in the spring on this stuff, okay, I had a question that was similar to this. And it took me, using work energy theorem, a grand total of 15 seconds to solve it. But if you did it using all the forces and doing all that calculation, it could have taken you up to 10 minutes. Okay? A number of people complained about how long the test was. I'm like, any of you who did this question with work energy theorem have a hard time completing the test? And they're like, no. Like, that's because it only took you 30 seconds to do that. And that's how long it should take you. Okay? If you understand work energy theorem, it's a quick question. If you don't, you'll still get the same answer, but through very convoluted routes. Okay? All right. This is an example of a physics 20 level work energy theorem question. Okay? In this question, the mechanical energy, both potential and kinetic, is changing. Unlike in Science 10, where you would have only had questions where either potential was changing or kinetic was changing, but never both at the same time. Okay? It's okay that both change. It doesn't really change what we do. All right? So I want you to copy this question down right now, and then we're going to walk through it together as an example of the type of thing you could be asked on work energy theory. Okay? Give you a couple of minutes to get that written. Okay. So first off, quick review. What's work? Change in something. Mechanical energy. All right, so it's a change in mechanical energy. How do I calculate mechanical energy? It's the sum of what? The sum of the potential energy of an object plus the kinetic energy of the object. Okay? And how do I calculate the change in something? Something minus something. It's always Final minus initial.
Minus.
Yeah, final minus initial. So what we're really saying here is that work is the final mechanical energy minus the initial mechanical energy. Okay, so I'm going to kind of expand this out as we walk through this question, because all this question is asking me to find is how much work is done on the block as it moves up the incline. Okay, all right, so I've got this part here. Now, we just said that mechanical energy can be calculated by adding the potential and the kinetic energy together. So that's going to look like this then. The potential energy final plus the kinetic energy final minus the potential energy initial plus the kinetic energy initial. Is this starting to look a little bit like a law of conservation of energy question? Like the roller coaster ones you did last year? It's because they work on the same idea. In a roller coaster question, the energy doesn't change, so those two things are equal. Here they're not equal because I'm changing the energy. I'm doing work. Okay? All right. I've got to expand this even further now. Okay? Do I have a formula that calculates potential energy? How do I calculate potential energy? Multiply three things together. Mass, gravity, and height, vertical distance. Yeah. Okay, so I'm going to have then m times g times h final plus 1/2 mv final squared. Okay, that's my potential energy final, that's my kinetic energy final. The sum of those is my mechanical energy final. Okay? I'm going to subtract from that to find the change in energy, the amount of energy I had at the beginning of the question. So that'll be m times g times h initial, that would be my initial potential energy, plus 1/2 mvi squared, my initial kinetic energy. Okay, that's work energy theorem. Work's a change in mechanical energy. Now I've got it expanded out as far as I can. Now I look at the question and I decide what kind or kinds of energy are changing in this question. Obviously mechanical energy is changing. Okay? So in this question, I've got a box at the bottom of a ramp moving at 1 meter per second. I'm going to accelerate it up the ramp. Okay, so I'm pushing it up the ramp really hard. It's accelerating up the ramp. Okay, not just going up at a constant velocity, accelerating. It's going to be going faster at the top of the ramp than the bottom. If that's the case, is the kinetic energy of the box changing? Yeah, its velocity is changing. I'm doing work in making this thing go faster. Okay, what about its potential energy? Is that changing? Definitely. I'm starting at the bottom of the ramp. I'm ending near the top or somewhere that's not the bottom. Okay, I'm going to have more potential energy there. So both these types of energy are changing, both kinetic and potential. Okay? Are any of these energies zero? Which one?
Initial potential.
Right. My initial potential energy is zero because I'm where? I'm at the bottom of the ramp, where my height is zero. So I can make my life a little bit easier by recognizing that and saying, I don't need to have that. Okay, it's zero, so I can just take it out of there. Okay, do I know the mass of the box? 1.20 kilograms. All right, so I know M. Okay, do I know G? Well, they didn't outright tell me this, but I'm going to assume this is happening on Earth, where I do know what G is. Okay, do I know the final height of the box? Yeah, they tell it to me right here, 0.850. Okay. Do I know the final speed of the box? Yeah, right here, 4 meters per second. So I've got everything in the first set of brackets. Okay. Second set of brackets is dealing with the bottom of the ramp. Well, I already know the height there, 0, bottom of the ramp. Okay. But I also know the speed of the box. Okay. So I know everything that's left in my formula, which is good, because now I need to just plug in those numbers and solve for the change in energy between the bottom of the ramp and the top of the ramp. In other words, how much work am I going to have to do to make this box do this? Okay, to accelerate up this ramp. So now it's just a matter of plugging in my numbers. All right, so 1.20, okay, the mass of the box, times 9.81 times the final height, 0.850, plus 1/2 times 1.2, okay, times 4 squared. That's my final speed. Okay, so there's my first set of brackets. Okay, now I'm going to subtract from that 1/2 times 1.2, the mass of the block, it's not changing, okay, times the initial speed of the block, 1 squared. So 1.2 times 9.81 times 0.85 plus 0.5 times 1.2 times 4 squared minus 0.5 times 1.2 times 1 squared. Oh, did I mess up a bracket somewhere? Yep, I didn't put a bracket here. Okay, this is going to take 19 joules worth of energy in order to happen. Okay, so is it a little bit involved? It is, okay? But again, there's nothing really difficult about the math. We didn't even really have to manipulate anything. You might have to in a more complex problem. Like maybe I tell you that 200 joules worth of energy is used, and I ask you to calculate how fast the box is going at the top, or how tall the box is. Well, then you'd be solving for one of these variables within this, and you'd have to manipulate a little bit. Okay? But it wouldn't be any different than what you would have done in Science 10 when you did a roller coaster question. Same kind of manipulation. But that's work energy theorem, okay? That's one in which both kinds of energy changed, and we really didn't do anything different. We just identified that this was final energy minus initial energy, okay? And we did our calculations. Right, solve for it there. Any questions on how that one worked? Okay. Try number 1, it's not too tough. Okay? Just try number 1, see how you do with that one, okay? And then we'll talk about it probably tomorrow. You will have a quiz tomorrow. It'll be Newton questions, not energy questions.